Hey there, ladies and gentlemen. Hey there, ladies and gentlemen. I think I just cut off the first hey there. Um, I think this video is going to be pretty short. This little chunk of questions is a bit easier than the last chunk. Definitely going to be shorter than the notes video. The first part is predicting products. In order to do this well, you really need to know the basic 5 equations off the top of your head, and you have to be good at nomenclature. Man, nomenclature seems to keep coming up, and it will. So in numbers, and then balancing, of course, but balancing is probably pretty easy for you. So in number 64, it says we have potassium metal added to liquid water, and I always think of liquid water as HOH instead of H2O because that's how it reacts typically, with the first H acting like a cation. And if I have a single element, potassium and water, boom, single element potassium and water reacting, this looks like a single displacement reaction. And so this potassium is going to react with the water, but it's only going to kick one of the hydrogens off. Remember how I said this is a much better way to write it. So if you think of it as HOH instead of H2O, it's going to kick one of those hydrogens off, and you're going to have potassium hydroxide. And after you kick the hydrogen off, it's got to go somewhere. Well, it's going to be H2O. And this is where I remind you of the Hofmann-Coles. That's a CL. These are the diatomics that you all learned at some point, and I'm gonna, you know what? Watch this. Boom. Oh, that's so much better for the viewing at home. So the diatomics, Hofbrinkel or Brinkelhoff, these are the 7 elements that refuse to be alone. And so now that hydrogen is alone, it finds another hydrogen and pairs up with it. And that's pretty important because it impacts the whole balancing issue, which I came back and did in blue afterwards. But again, I recognize that this was a single displacement reaction because I had a single element, potassium, and a compound, water, and potassium could kick out either hydrogen or oxygen from the reaction, and it typically kicks out just the hydrogen. And the next one, we have strontium reacting with fluorine. Well, if strontium reacting with fluorine, this can't be a single replacement or a double replacement. The only thing this can be is a synthesis where they both come together. And since strontium's a +2 and fluorine's a -1, that balanced pretty easily. Number 66, aluminum reacts with a copper 2 nitrate solution. So first, I got to write the formulas carefully. Aluminum, copper 2 nitrate. That means copper's got a +2 charge, and there's 2 nitrates attached to it. And then this also feels like a single displacement, just like we had up here, where aluminum can kick out a single element. It's going to kick out the copper. And when I put the new aluminum and the nitrate together, I have to redo the charges. Aluminum's a +3, so there'd be 3 nitrates attached to it. And then the copper's by itself. Copper is not one of the Brinkelhoffs, so it can't be Cu2. It would only have a coefficient. It doesn't bond to itself automatically, that is. And so after I rewrite the formulas in blue on the right side, I then have to come back and balance the entire reaction, which is why the 2's were in red this time. Number 67, ammonium sulfide, ammonium NH4 plus 1, and sulfide, IDE, is the sulfur ion. And then lithium is Li, it's with dichromate, so these are both an ionic compound. Lithium's a +1, dichromate is Cr2O7 -2 charge. So here we go. This is those two formulas, ammonium 2 with the sulfur, lithium's 2 with the dichromate, Cr2O7's dichromate. What type of reaction does this look like? We have one compound and another compound. This looks like you got it, double replacement. So we do the double replacement, and we end up with Li2S because sulfur is still a -2 charge. And there's a typo in there. I knew I'd make a mistake at some point. This is actually wrong. Let's fix this. You know, it's okay to make mistakes, especially when you catch them. Don't mind making mistakes sometimes. Big fan of recording them, but there we go. I did have a typo in there. I made the formula for ammonium dichromate wrong. I think I was just typing it too fast when I made it. But so that's now balanced. There's 2 ammoniums and a dichromate. Awesome. Manganese 4 perchlorate is heated. So a lot of times when you have a compound like this and it is heated, those oxygens are going to break off. The oxygens and oxates and anything that's got like a nitrate or a chlorate, The oxygens break off and they're free. So you're going to have manganese and chlorine together and a bunch of oxygens that have floated off somewhere. And so since manganese is a +4, oh, that's manganese 3. Since manganese is a +3, there's going to be 3 chlorines attached to it. Then the oxygens are free. Why is there a 6 right here? That's a big number. Oh, that's because there's 12 oxygens. So 6 times 2 is 12. And then we have dicarbon dihydride combusts completely. So this is a combustion reaction. Combustion reactions are when a hydrocarbon reacts with oxygen. It could go one of two directions. If there's plenty of oxygen, we have complete combustion, which we do here. It makes carbon dioxide, and water. If there's a limited supply of oxygen, then it makes carbon monoxide and water. So since this is a complete combustion, it makes carbon dioxide and water, and then it gets balanced. There we go. Next page. Number 70, we have an average atomic mass question. Average atomic mass formula looks kind of like this. You see it a bunch of different ways. The average atomic mass that you find on the periodic table, which, you have all these elements on the periodic table. Each one has an average atomic mass on it. Those average atomic masses, and this is rhenium. Where the heck is rhenium? Rhenium, where are you? That's rhodium. Weird, I don't see rhenium. Oh, rhenium, I think, is down in the inner trans. Oh, there it is. 186.21. So that 186.21 on the periodic table is actually an average of a couple of different isotopes. And here they're telling us that rhenium has two isotopes. So the mass of one isotope times its percent abundance plus the mass of the other isotope times its percent abundance should equal the average atomic mass. And I like to be consistent, so I'm going to use the multiplication sign there. The X is a multiplication sign. So in number 70, they tell us we have these two isotopes, and here's the average, 186.207, better than that periodic table below. And it says rhenium is 62.60% rhenium, and there's the mass of that type of rhenium. Calculate the other. So if I know that there we go. If I know that mass 186.956, that's the isotope mass, has this percent abundance, 62%, which is 62 over 100, then the other one must be 37.4%. They've got to add up to 100% since there's only two of them. And so then I could find the missing mass. So again, this is the percent abundance, 62%. So the other one has to be the rest of 100. 37.40 is the rest of the percentage. And then I solved for the missing mass. There we go. Number 71, how many atoms are in 1 carat diamond? How many atoms? That's a question that involves Avogadro's number. Please remember that 1 mole of anything equals 6.022 times 10 to the 23rd of those objects. So we have a 1 carat diamond, which we know is zero point 0.2 grams. So I said, well, 1 carat equals zero point 0.2 grams. And then I converted it to moles. I used that zero point 0.2 grams divided by the molar mass of the periodic table for carbon. Carbon is 12.01, so that's how many moles of carbon there are. Notice I didn't do any rounding yet. Not really. My calculator left the whole thing. And then I converted moles into using Avogadro's number into atoms. So we have 1 times 10 to the 22nd carbon atoms. The density of the diamond is 3.51 times grams per cubic centimeter. What is the volume of a 5 carat diamond? Well, a 5 carat diamond would be 1 gram. Again, I used this ratio up here. 1 carat's 0.2, so 5 carats would be 1 gram. And then I said if I have 1 gram and I rearrange the density equation, density equals mass divided by volume, therefore volume equals mass divided by density. So I did mass divided by density, the grams divided by grams would cancel, cubic centimeters don't cancel, and I got the volume of a 5 carat diamond. Next page. Calculating molar masses. The molar mass is the mass that represents 1 mole of the substance, meaning you have 6.022 times 10 to the 23rd of that compound or molecule or atom. And so here we have a whole bunch of compounds. I have to make sure I have the formula right for the compound. Ammonium dichromate. This is actually one I messed up earlier. It's NH42Cr2O7. I got it right the second time. Go me. So in order to figure out the molar mass of this compound, I've got to look up those pieces. There's NH4 times 2 and then Cr2O7. So here's the NH4, and I just put a 2 in front to multiply NH4 times 2. That's nitrogen plus 4 hydrogens. And then I got the 2 chromiums and the 7 oxygens, and I got a walloping 252 for its molar mass. Calcium phosphate, again, I have to work out the formula correctly, Ca3PO42, and then I got to look up each piece. Now, these shouldn't be terrible questions. You have to work out the formula. That's a minute. If you know your polyatomic ions, it's even less. Um, Then you have to put together the molar masses from the periodic table. I expect that you know oxygen, you probably know hydrogen, you should know hydrogen. Maybe you have to look up nitrogen, but chromium, you definitely have to look that one up. Phosphorus, you probably have to look that one up. Calcium, you probably have to look that one up. And then you use them after you look them up. But hey, Mr. Murphy, yes, you with the glasses. Is it okay if I distribute this too for math purposes? Yeah, for math purposes, you could say 2 times phosphorus and 8 oxygens. That's totally fine. It's the same thing. But in reality, the PO4s are connected to each are two separate PO4s attached to the calciums. Then we have 2 sodiums, a hydrogen, and some phosphorus, and 4 oxygens. Add it all together. There you go. And they got to distribute that too. So 2 times 1 plus 12 plus da, da, da. And so that's how you do molar masses. And this was probably a pretty easy sheet for you. Let's go on. Let's see, the molecules of chlorohydrate, a drug formerly used as a sedative and hypnotic. How many moles of chlorohydrate are in 500 grams of chlorohydrate? The first thing you have to do, of course, anytime you're dealing with moles, is probably figure out a molar mass. So I went and grabbed 2 carbons, 3 hydrogens, 3 chlorines, and 2 oxygens, and added them together, and I got a molar mass. I kind of just set that molar mass over here because I might need it a couple times. And so if we have 500 grams divided by the molar mass, grams divided by grams cancel, moles don't cancel, and I have the moles of chlorohydrate in 500 grams. It's only about 3 moles. Huh, that's a big compound. What is the mass in grams of this many moles? Well, that's not too bad. We could set it up. We could say, well, I wrote it longhand instead of scientific notation. 0.020 moles. There's 165.4 grams per mole. I have that many grams, 3 grams. 3.3 or 3.1. Which is the right answer sig fig wise? This is the better answer sig fig wise. This answer is perfectly acceptable also. Remember, you're allowed to have one extra. All right, number 78. What is the mass of 500 molecules of chlorohydrate? Okay, well, these are molecules. So the first thing we're going to do is change the molecules into moles. So I have to grab Avogadro's number and say 500 molecules. There's a whole lot of molecules in 1 mole. And then I could change moles into grams. I am expecting a very small answer because 500 divided by ridiculously huge is insanely small. So regular number divided by gigantic number equals super small number. And the last one for this video, told you it was going to be short. Determine the percent composition by mass of chlorohydrate. I've only done one of them, but percent composition is the part you care about divided by the total. And I decided to do the carbon. There's 2 carbons in there. So this is 2 carbons divided by the whole molar mass. And I got 14.5% carbon. You could repeat that for any of the elements. You could say 3 hydrogens divided by the total, 3 chlorines divided by the total, 2 oxygens divided by the total. And like last time, I am going to give you a second on each page. Let me go back to the very first one. Nope, that's horrible looking. And here we go. Pause for a second. And the other 2. And I'm pausing for a second. And here's our molar masses. And the last molar mass. And then this last page where we had to find the molar mass, and pause for a second. And the last one. All right, I will see you in the next video in just a couple of minutes.